Hey scholars, good to be back with you, and I'd like to talk to you today about a different kind of pickup than we talked about last time, and this one is called a humbucker. Now if you remember from last time, or maybe go back and look at the last video, we went over a kind called a single coil pickup. Single coil pickups are in a lot of the early electric guitars, and they're still in a few of them, but they have a problem. They hum. The wire in the pickup acts like an antenna, and it's sensitive to the 60 hertz noise that's in all the buildings. Now if you're in a different country, it may be 50 hertz, but whatever the mains are, there's an alternating current going through the mains, and the pickups in the guitar can pick that up and they hum. They go hmm. Alright, so we want to get rid of that, and there's a design called a humbucker, and the humbucker was developed in, I believe, the mid-50s by a guy named Seth Lover. It was very, very clever, and it uses a principle that electrical engineers now call common mode rejection. So if you've heard of common mode rejection, you kind of know what a humbucker is. So here's the size of a single coil pickup, and I'll hold this up so you can see it. That is a bobbin, okay? The little holes there, there's going to be, in this one there's going to be 6 magnets that go through there, 1 magnet for each string, and that's where the wire goes on. Now this wire is really tiny. I told you before, let's see, this wire is, let's see, this is 38 gauge wire, okay? So this is actually pretty coarse wire. This is pretty big for a guitar pickup. I don't know if you can even see that. I don't think you can, but that's what 38 gauge wire looks like. And I've seen, let's see if I can, maybe you can see that against my shirt. There you go. That's 38 gauge wire. I've seen pickups wound with 44 gauge wire, and the way English wire sizes work, it's basically the number of wires you can grab in a bundle, so a larger number means finer wire. So 44 gauge wire is like almost human hair sized wire. So that's what's going on. There's 6,500 turns nominally. That means a couple of thousand, 5, 6, 7, 8,000 turns, something like that in one of these. The number I keep seeing is 6,500 turns as being kind of the nominal. When people say, oh, I've got a really hot pickup, well, hot means it's got more turns in it, so it's more sensitive to the moving electromagnetic field and has a higher resistance. So you can actually use a volt-ohm meter, measure the resistance across a pickup, and if the resistance is really high, people say, well, that's a hot pickup in that it's more sensitive to string motion. So we got the problem here that we've got, the thing is sensitive not only to the motion of the string, but also the electromagnetic field around you. Well, how do you fix that? Well, the idea is you make 2 coils that are equally sensitive to the string motion, but oppositely sensitive to the electromagnetic field that's just in the room. How do you do that? Well, here's a way to do it. Here's a blue pen here. Okay, let's take here's a magnet. And I'm just going to draw this for the equivalent of 1 string, and then we'll go over how it works for a pickup that has to sense all 6 strings. So there's a magnet, and let's say it's polarized vertically north to south. Doesn't matter which one this is, but we'll just call it that way. And we'll bring wire in here and we'll wrap it around. Okay, now I've only got, let's see, 1, 2, 3 turns, I guess. 1, 2, well, 2 turns, I guess. Because there's really 6,500 in here, I don't want to try to draw all 6,500. The point is that this wire, if we're looking this direction on the wire, if we're assuming electron flow basically is that direction, here's the direction of those coils. That would be counterclockwise. Well, if I were to bring this to another coil, another magnet right next to it, all right, now I've got to, the way this is going to work, I've got to go in here and I've got to go, let's see, I'll make sure I do this right. There we go. I think I got this now. Now the wires go in the other direction. If you're going through the wire, and now it's going this way. Now it's clockwise. The flow through the wire goes around that coil clockwise. All right. Now I've reversed essentially the polarity, the sensitivity on this coil right there. So this coil and this coil are oppositely sensitive to the magnetic field. Okay. So any signal induced, now when I say magnetic field, I mean there's waves coming in and this is, I'll just call this the field, hopefully you can see that. And that field comes from the electric power that's run through the buildings. It's called mains power, and it's an alternating current. So the signal's already always oscillating at 60 hertz in the US. It may be 50 hertz where you are. But that field is always there. Okay, we try to ground it, we try to shield it, but it doesn't always work. There's 60 hertz noise in all buildings in the U.S. all the time, unless you go to fairly heroic efforts to get rid of it. Well, we don't. There's plugs everywhere, so we see this everywhere. So now I've got a system that's any field or any signal induced over here because of this field, I'm going to induce the opposite signal over here because the coils go in the other direction. So any signal that comes from the field cancels out. The common mode, the thing that both of these coils sees, cancel out because there's essentially a negative sign on what this coil sees. There's one problem right now. Unless we're clever, it's also oppositely sensitive to the string. So right now it won't see the field, but unless we're clever, it's not going to see the string either. And here's how you fix that. Reverse the polarity of the magnet. Now that one's north, that one's south. So as the string moves, this coil is oppositely sensitive to the string, but the magnetic polarity reversed. So this sees the string with the same phase angle that this sees the string with, pretty much. Okay? So you get a system that is oppositely sensitive to this. Okay? So this coil and this coil cancel each other out. They reject the common mode. But because the magnets are polarized in opposite directions, they're equally sensitive to the string motion. So they hear the string, they don't hear this. And Seth Loverd worked for, I think, Gibson at the time, and the name was they gave that kind of pickup was called a humbucker. It got rid of hum. And here's what a humbucker looks like. Okay, now this is a copy made, I don't know where, probably it's imported, I think, I'm not sure where it was made. This is what the traditional humbucker looks like. And what it's got is two coils. You can see there's one, there's the other one, and they're the same size as the other one. And you can see these little pole pieces. Now the difference is these actually aren't magnets. These are unmagnetized pieces of steel. The magnet lives behind this plate, and I'll draw that here in a second. These little metal tabs here, right there and right there, are the tabs that let you mount it into the guitar. And this is just the wire that comes out. And then on this one, there's only two wires. There's all kinds of different ones here. See if I can get that. That's the signal and that's the ground. There are other kinds of humbuckers that have more wires coming out of them. If you care, you can send me in, leave some comments on the YouTube channel if you want to hear more about what all these wires do. I can tell you that as well. Okay? So there's what it looks like. Now, this is nice. This is nice and tidy. It's twice as big as this one. It uses two of the same kinds of coils, same kinds of bobbins. You can see those are the same size. Okay, the way the humbucker was designed, rather than trying to stick 12 magnets in here, which you could do, I mean, I think it'll work. They decided to make Seth Loverd and I guess by extension Gibson. Now, when I say a pole piece, it's just a piece of iron or steel. I'm not sure what it is, and it's almost all iron. Even steel is 99% iron. So it's you can magnetize it. You can make a magnet out of it. If you connect a magnet to it, it'll stick. Okay, it's ferrous. And what they did is instead of putting those 12 magnets in there, they put another magnet in between them. All right. And so I don't know which way this is on. One side is north and one side is south. But when you look at the magnet, it's very long, and it's actually polarized across the short axis. And there's more of these up here as you go. And they're connected to they're touching the magnet. So if you look at this, if you were to take this apart, okay, the magnet is behind there. It's about that wide and about that high, but it's polarized that direction. We normally think of magnets as being polarized across the long direction. They don't have to be, and this one isn't. It's actually polarized that way. I found a cutaway of a single coil pickup, so you can see what this looks like. And that shows the 6 pole pieces. And I also found a cutaway of a humbucker pickup that shows that rectangular magnet in there that's polarized along the short axis. And this is what it looks like. Okay, so the last thing to go over here now is just sort of terminology. This thing is the classic humbucker design, and it gets called a couple of different things. Sometimes they call this a 59 humbucker. Well, what's 59 mean? Well, it was designed, I guess, or released, I'm not sure which, in 1959. Okay, and so there's a lot of copies of these out there. They're generically known as 59 humbuckers. The 59 humbucker is actually a Gibson product. If you want an original, an authentic one, you have to go buy one, I believe, from Gibson. But there are other copies of it made. Okay, and they're very faithful copies. The thing to remember is that modern manufacturing technology is good enough that even an inexpensive modern pickup could be better than an old one. The magnetic materials weren't that good, the wire might not have been that good, the insulation around the wire is probably better now. It's polymers rather than shellac or lacquer or something. So a modern pickup, there's no reason to think that you could have a quality problem with a modern pickup. I would probably recommend them. There are single coil sized humbuckers. All right. Now, if there's any problem with this, it's that when you look at this, it's sensitive to the string, but it's sensitive to the string over a distance of about that, about the width of my finger, and that's called a window length. Okay, that's how much of the string the pickup is listening to. Well, the shorter that window length is, the more high frequency sounds you get. And that can be another video someday if you want. So there's a reason you would want this humbucker to be this size, because it'll see a shorter section of the string. Well, there's single coil sized humbuckers, and there's a couple ways people do it. One is they'll stack the coils one over the other, and this is what that one looks like. Okay, that's a stacked pickup from Seymour Duncan. Seymour Duncan is a manufacturer of very high quality pickups. They're kind of the, I don't know, probably the BMW of the pickup world, if you want to think about it that way. Another way to do it is just to make it in this configuration, but just make the coils a lot smaller. Okay, and Seymour Duncan has one called a Mini 59. It's built to match that 1959 style pickup, but it's the size of this one, so it'll fit in a single coil pocket or mounting on an electric guitar. And this is what a Mini 59 looks like. So to the user, those will sound brighter. Okay, brighter means it's got more high frequency content in it. The reason it has more high frequency content is it's smaller and is looking at a shorter section of the string, so it can see higher frequencies, mode shapes that have shorter distance between the node lines is really what it boils down to. And again, if you want a video on how pickup design changes what you hear, I can do that too. So there you have it. There's last video we went over single coil pickups. Now we know about single coil and humbucker pickups and how they get rid of electromagnetic noise for us. I hope this helps, and I'll see you next time.